Hello interwebs, welcome to Let's Fix Computers. I've got a MacBook Air here. This is an A1468, and the A1468 is kinda done, really. This chassis is a decade old. It didn't really have any meaningful changes between sort of 2013, 2014, all the way up to 2017. And then 2018, I think, is when the MacBook Air Retina came out. And by the time 2017 rolled around, the A1468, unchanged as it was for the past few years, was really looking tired. So this particular one, I think, is a 2017 model. But despite being 2017, the hardware in it is older than that. So for sort of 2016, 2017, these MacBook Airs just have aged really badly, to be honest. The huge bezels on them and stuff look incredibly dated. The screens on them aren't very good, especially when compared to all of the other Apple laptops, which were all Retina by sort of 2013 onwards. However, also, because these things are so common, because there's so many of them out and about, you will see them in for repair quite often. And it also means that they are meticulously documented. There is so much information about this chassis and this logic board on the internet that this does actually make them really good candidates for learning laptops. So I figured when this one came in, I was like, okay, well let's fix this and make a video on it anyway, because it's kind of a good showcase on showing off some of the tools for starting to learn to fix computers. So this might be an easy one. I have suspicion this is another wretched capacitor, but you never know. Maybe we'll get an excuse to show some other measurements and stuff. Let's get into it. Starting out, I've got a Type-C to MagSafe cable plugged in. We've got a light on the charger, but as you can see on the left, we're getting about 39 milliamps or not. That's actually like low 30s because this Type-C to MagSafe adapter pulls a couple of milliamps itself. So that's actually sort of low 30s. And we're just stuck in this state. And this sort of sub 40 milliamp power draw, this is a very common state that these things will get into when the logic board is just in a state of, I am not ready to power up. So let's disconnect that. And I'm going to take the back cover off and we're going to do a visual inspection on the inside and see what we can find. So I'll roll the intro to the video while I take the screws out the back, and then we'll have a look inside. Right, we're going to check our dust patterns. So honest dust on the inside, lots of dust, but dust tells a story. So there's a few marks there. I don't know. I don't think I just put those finger marks there, so it looks like it's probably been opened before. But there's no watertight marks. We've got a little bit of corrosion just around the back here. That could be telling us something. So that was about there-ish. And I don't see anything. I don't see any corresponding marks on the laptop itself. So there could be something on the other side of the logic board there. Looking at the laptop itself, again, we've got lots of dust. I'm looking for craters, explosions, anything like that. Again, I'm not really seeing anything, but also just there's enough dust here that could be concealing things. So let's disconnect the battery, and the first thing I'm going to do is just check for any screaming short circuits. So we're going to check the main power rail and see where we go from there. So let's zoom in a little bit and turn on the multimeter into resistance mode. Now on these older MacBook logic boards, the main power rail was infamously called PP-Bus G3 Hot. So we're going to check our PP-Bus. So I'm going to open up Flex Board View with some schematics, and I'll show you how we can find that. So in Flex Board View here, I've got a view of the board, and if you want to know how to find this, you need to Google search for the board number and schematic. So to find the board number, we've got to find it on the board itself. So on these ones, it's under the SSD. So let me just quickly take that out, and I'll just show you where to find that. If this turns out to be a very easy "it's another capacitor" video, then at least I can show off some of the basics in getting started with board repair for this one, just simply because these are questions I get asked all the time, and it's really annoying to answer them in comments. So under the SSD there, you can see just about. Okay, there's a number there. I can't see how well that's coming out on camera, but it says 820-00165-A. So the -A indicates a version of the board, and that will often correspond to how much RAM it has and things like that. But the 820-00165 is the bit that we're interested in. And on other MacBooks, this number could be anywhere. Just look around the board somewhere and eventually you'll find it. Let me grab another random logic board. Right, here's a random MacBook Pro logic board. And there it is. There's our number on the board there. So this board is that way round, and that's an 820-01041. So that one was there. So basically just have a look around the board. It might be under it might be hidden somewhere, so if you're not finding it, you might have to look around. Anywho, let's put that away. We've got our schematics open and we need to find the main power rail. So I'm going to Control F and I'm going to search for ppbus _G3H, which is G3 hot. There's my search box, and show me that. So we're looking at the top side of the board, which is the upper half. Flex board view shows me both sides at the same time. And if we zoom in on here, we've got this fuse here. So this is the main fuse for the main power rail. So it's a great place to look at to check the main power rail. And so what I'm going to do, I'm going to turn this around so it's in the same orientation that I'm looking at the actual board in. So let's just turn. There we go. So there's a big inductor here, L7130, and just above that is F7140, which is the fuse we're looking for. So back to the board, and in roughly the same place, there's the big inductor, and just above that you can see we've got a little fuse. So I'll just measure that. So I'll put my black probe on a ground point. So I'm going to pick the negative side of a capacitor, and let's check that fuse. And yeah, we've got a main rail short. So we're looking for less than 1 ohm. This rail should be in the thousands of ohms. So 0.16 is definitely a short. Is the fuse itself okay? It probably will be. These fuses just... Oh, okay, never mind. I was about to say these fuses never blow. But yeah, the fuse has blown. Okay, fair enough. Right, so the main power rail fuse has blown because there is a short on it. So let's take a closer look. So on the schematic here, if we look at this side of it, this left side, that's PPVBAT G3 hot, charger regulated, and that is going back to this section of the board, which in turn goes all the way back into here, and this comes back to the charger and the battery connector and stuff like that. After it goes through all this regulation, it becomes the main power rail where it goes off into the rest of the laptop to power stuff. So let's look at this on the schematic because it's easier that way. I'm going to right click on this and search schematic, and Flexboard View will quickly find it on the schematic for me. So as you can see here on this big page here, this whole page is PP bus supply and battery charger. So here we've got U7100, which is the regulator that handles it handles my phone going off. Hold on one moment. So this chip is running everything on the page, and if we look up in the top right of the screen, you can see we've got this bit saying from adapter. So this is where power comes into the laptop from the charger, and it's going to go through these MOSFETs. It's going to come down here, and it's going to go into this dual MOSFET package, and then through an inductor, and then into the fuse and become the main power rail. And likewise, down the bottom here, we've got this section that says to and from the battery. So this is where our battery connects into the system. And there's a MOSFET controlling that. And then this again can come up, round, and into the fuse and out as the main power rail as well. And because this is to and from, this is bidirectional. So power can come out of the battery and go into the main power rail, or the power coming from the charger can go down and into the battery to charge it. So this whole page is a really good showcase of buck regulators and just how straightforward main power rails in laptops can work, because you've got the charger and the battery just all in one place in one system as one circuit diagram. So it's a really cool exercise to study this page of this schematic and see if you can figure out how it works. I'm going to talk more about these in the future, but also if you look at my old board repair basics series, the old stuff, I believe that I have a video that talks about this page, albeit probably from an older MacBook, but whatever. I'm not going to go into granular details here. This is supposed to be a very flying overview rather than an hour-long video. This is supposed to be a teaser, just here's some insights into stuff that you could look into if you're interested, you know? So yeah, anyway. So we've gotten to this fuse. Our output side is shorted and the fuse has blown. So all of this side is going to be okay because the pin 2 on the output side was shorted. So let's see where our short is. So going back to the board view, once we come out of this fuse, we go into a couple of places all across the board, but the main two places we go up to is we go up to F7700 here, and we become the LCD backlight system, and then also we then go into R5450. Now, R means resistor, and a 4-pin resistor like this is going to be a current sense resistor. And if we go back to the circuit diagram, a current sense resistor looks like this guy here. Here's R7120. And what this is, it's a very low value resistor. I've talked about these in previous videos. As power goes through this resistor, there will be a very, very small voltage drop depending on how many amps are flowing through it. So the higher the current, the higher the voltage drop will be. But that voltage drop is going to be minuscule, so it doesn't affect the computer in any meaningful way. But pins 3 and 4 here are 2 sense wires connected to each side of it. And these go back down to the control chip here. And the control chip is watching those sense lines and watching how big that voltage drop is. So by measuring the voltage drop across this tiny value resistor, the control chip knows how much current is flowing through the system and thus how much power the laptop is drawing. So R5450 here is going to be another current sense resistor. So if we have a look, if we see where that goes to, that goes through this resistor, and then it becomes this rail here, PP5 S5 HS computing, and that goes across to all of this stuff over here, which basically links into CPU vCore. This is the CPU power system over here. Now, all of these capacitors have a tendency to blow as well, and when these ones are tantalum capacitors, so when these blow, they'll often go with a bang, and I've seen quite a couple of these boards where one of these guys has exploded and literally just left a black mark in its place. And when that happens, there'll usually be a pop and you will smell a burning magic smoke smell. So if you've got a customer who says, "I smelt burning," then you immediately want to open it up and look at these capacitors, because yeah, I've replaced these a couple of times. Okay, so we've also got all of this stuff. These capacitors are on the same rail. These go to auxiliary power rails. So some of these auxiliary power rails go into the CPU as well. Some of them go into secondary rails. So for example, here we've got PDDR, so there's the memory power rail. This guy over here, we've got P3V3, so that's the 3.3 volt rail. Somewhere around here, we've got the 5-volt rail. I can't remember where that is off the top of my head, but it's close by. It'll be in here somewhere. And so on and so forth. It might be that one. Nope, that's one VO5, so that's a 1-volt rail. But you get the idea. So we've got a lot of places that this main power rail is now powering, and any one of them could be the suspect. Any one of them could be our culprit. So what we'll do is we'll quickly buzz across all of them and just check if any of those are also low resistance, because that tells us if our fault is on the main power rail or on a secondary power rail. So we're going to come back to the board now, and I'm going to check all of the secondary power rails. So that means all of these grey squares, all of these inductors. So we're going to check this guy here, here, here. These two over here, these are going to be going into CPU vCore. We're expecting these to be low resistance because the CPU is always low resistance. So let's have a quick look. We'll start there for good measure, but again, these are not really relevant. So yeah, 27 ohms, that's very low for a power rail, but again, it's CPU vCore. We kind of expect that. So let's go over to these other ones. So let's check here. So we've got kilo ohms. We're in the kilo ohms range. Again, 10 kilo ohms. It'll settle, but it's still in the kilo ohms range. Kilo ohms and 24 ohms. Again, kilo ohms, that's fine. And also, one more. We've got the backlight up in the top left. And that is at kilo ohms. So, yeah, that's not our problem either. All right, so all of our secondary power rails look good. So we've got a main rail short, and we don't know where it is. Right, so before I go any further, I'm going to actually take the motherboard out of the laptop, because there might be a crater on the bottom of it for all we know. So let's do a little bit of fast forwarding while I take this board out, and we're going to check the back of it before we go any further. I should have done this earlier on, but I was basically still assessing. So sometimes you can tell a lot before you even get the board out the laptop. Right. Looking on the back of the motherboard, we've got more honest dust. No screaming problems that I can see, though. All right. So I'm going to give this a brush down, and I think we're going to set up for power injection. So I've just brushed down the board and just brushed all of this dust off, so it's looking a lot cleaner now. And I just used a common paintbrush will do for that. Assuming you're not in, like, you know, the Arizona desert where you actually need to worry about static. And now the dust is removed, we've got more information here. So if I hold it there and hold it in the light, see if you can spot the problem here. All right, the problem is there. Can you see that little shiny spot above those capacitors? Let's look closelier. Now that's probably our issue. So one of those tantalum capacitors has had a tantrum. The question is, which one is it? Hard to tell from here because I can't see down the sides. If I had to guess, I'm going to say it's the middle one, and I think it's got a crack in the side and it's gone out to the side. It's splurted its guts out in that direction. So I think that middle one has died. So I'm going to actually just take a pot shot at that and take it off the board. Right, so we could hot air this off the board. However, tantalum capacitors don't like hot air, so it's nice to avoid it when you can. So I'm going to come in with my hot tweezers instead, and I'm just going to just touch up both sides here with some fresh leaded solder. And we'll just let that work in and ease this guy off the board. These guys can weld themselves down, so it might fight me a bit. Come on, dude. You're moving. The ground side is fighting me. There we go. Right, now that guy's gone, let's go back to our fuse, and I'm going to put my black probe on the ground again, and we'll just check that. And hey ho, we now have kiloohms. So yeah, that was it. Okay, right, we still have a blown fuse here. So I'm measuring in resistance mode here, and being a fuse, this should be a wire, and it should be showing me 0 right now. So this guy is blown. You can see there's sort of black speckling on it. You can see this guy has kind of exploded. So that guy's also gone bang. So we'll take that off the board as well. And this dude, you can use your regular soldering iron. If you've got a knife edge tip like me, you can kind of just do a hit and run on this one. So I'm just going to pile some solder in on both sides here. And we're just going to heat both sides at the same time and just knock this guy off. Getting some tweezers ready for when it gets stuck against the inductor. Wow, or you could be completely stuck. That's cool. There we go. Now I'm going to put some flux on these pads and on where the capacitor was, and we're just going to wick down these pads, and then I can put down a new fuse and a new capacitor, and we can do that just using the iron and avoid using hot air around these other capacitors. Damn it. And then I soldered the wick down. All right, we're fine. Oh, a little bit more there. Come on, give me that little bit on the edge. Good enough. And over here. Nice. Coming in with the earbud. In the US, the brand name is a Q-tip, but we call them cotton buds or earbuds because you put them in your ear, even though every doctor will tell you not to put them in your ear. Nice. All right, now we've got some clean pads. Now we need some donors. I'm going to grab one of my donor boards. Coming in with a donor board here. This one is a 820-3437. This is from a slightly older version of this board. However, they're almost identical. The 3437 and the 00165 are extremely similar. This is like the 2014 versus the 2015, 16, and 17 or something like that. But this one is close enough that we've got the same row of capacitors and we've also got the same fuse in the same place. Wow, look at that grot. That's horrid. Let's just brush this down. Alright, so now I'm going to take the same parts off of this board and then we'll put them onto our repair board. I'll turn the board around so I have a better angle at it for this one. Oh. There we go. And just put some alcohol across that and toothbrush it down. Cool. So let's take our same measurements again and just check if we've improved things. So I'll put my black probe on a ground point again. And so firstly, let's go over to the fuse. And our main rail short is still gone. 120 looks kind of weird. But we were seeing kind of low resistance over here earlier on. Let's see what happens. I'm going to check something else in a minute. However, also our fuse has been replaced, so is now no longer blown. So we now see a straight through on the fuse. I'm just going to check what kind of readings we should be getting here. In Flex Board View, I can download the board data, which will show me known readings for this area. So these readings here, this 0.13 that we're getting, and 0.137 there, these are diode mode measurements that are uploaded to open board data. So if I set my multimeter into diode mode, and I'm going to put my red probe on ground, and my black probe on the fuse. And when we measure that, we get 0164. So that's a little bit higher than what we're seeing on the reference, but it's not a billion miles out of spec. You know, we're not reading orders of magnitude out, so that's close enough. It's been a hot minute since I've looked at one of these boards, so I can't remember if that's normal or not. I would expect to see a higher resistance, but I'm going to power it on and see what happens. So we could take the I/O board out and connect that up and then power it out of the chassis. However, at this point, I think it's going to work, so I'm just going to put it back in the chassis. And if we get a fan spin off of this, we'll then take another quick look at the schematic, and I'll just show you guys what I actually did one more time, just for good measure, just so you can follow along at home. While I'm plugging these annoying wires back in, I just want to have a quick note about observer bias. I make jokes about how often I'm just replacing dead capacitors on this channel. And there's a bit of a mixture of that because, like, lots of people can very easily believe that that is just all you'll ever see. And now, don't get me wrong, dead capacitors are a really common fault. And like, I was actually hoping this would be a bit more complicated than that, but there it is. But the thing is, they're not all you will see. And for every easy, low-hanging fruit repair you see me doing, there was also just the no fixes that just went nowhere, that you don't see because it wasn't a capacitor and it was some nightmare horrible rabbit hole. And sometimes I end up getting a fix out of those and sometimes I don't. So I want to make note that while dead capacitors are a very common fault, but they're still not the only fault you'll ever see. And I also have an inherent advantage in my line of work because where I'm running a high street shop, I have the advantage of being the person who usually gets the first crack at the whip. Whereas if you're like buying broken stuff or looking for broken stuff, you're often going to end up finding things that everyone else has already given up on because it was a nightmare rabbit hole. So do keep in mind that while this is a common fault that you can see very often, it's by no means the only kind of fault that you'll see. And our survey says green light on charger. And same deal, yeah, it looks like that low. Let's go to voltage and just see if we're getting our main power rail. So black probe on ground. I'm just going to check that fuse. No, 8.6 volts. The main power rail is up. Okay. I think the 00165 wants a battery, so let's plug the battery in. There we go. Now we have fan spin. Yeah, it wanted the battery. I think the 3437 doesn't need the battery, but the 00165 does need the battery. So we've got fan spin, we just had a chime, and if I open that up, you can see we've got an Apple logo. There we go. So we replaced this capacitor here, and if we zoom down on that, we've got ground on one side of it, and on this side, that is part of PP-Bus S5HS computing. So that was the rail I told you about. Remember how I pointed out all these capacitors over here? Well, yeah, it was this guy here, and that ties back into that current sense resistor, which then goes back to the fuse. So if we have a look at the schematic, I'll right click on that and search for it. That is over here, and that is part of the 1 volt regulator. So up here we've got PP-Bus S5HS computing iSense, so that's functionally our main power rail, just under a different name. And that's coming down here and going into a dual MOSFET package, and this is a buck regulator that is then chopping that down into a 1 volt output. However, up here, these are the input capacitors for it. These provide smoothing and power bypass for this buck regulator. So that was the guy that had failed, and it was a 62 microfarad 11 volt tantalum poly capacitor. So there we go. Right, thank you everyone for watching. I'm going to put the rest of the screws in this and put the back cover on, but you don't need to watch me do that. Thanks a lot, and I will see you next time. Bye for now.